In this video, I'm going to dive into the 4 special cases. We'll use these cases to help round out our interaction diagram and define the boundaries. So in condition 1, we are going to set our bottom steel strain equal to 0. This is when the maximum strain at the extreme compression fiber reaches 0.003 without the bottom strain experiencing any stress at all. So you can see a screenshot from the ACI commentary that shows the strain diagram and the force diagram for the section to model this. So the first thing we do with this is we back calculate C, the distance to the neutral axis, using strain compatibility, or the similar triangles, which can be rearranged to the equation I've shown here, ECU times D1 over negative ES1 plus ECU. And in this case, ES1 is 0. So C is just going to be equal to D1, or the distance to the centroid of the bottom steel. And then we can back calculate C by setting ES1 equal to 0. We can use the equations from the previous video to back calculate all the terms needed for axial and the flexural capacity of the section in this special case, and we can plot this point on the diagram. We'll do the same thing for conditions 2 through 4, with bottom steel strain as the only term changing. So condition 2, bottom steel strain is half of our yield strain. In this case, we can calculate the yield strain as Fy over ES and then divide by 2. Condition 3, bottom steel strain is set to its strain limit for a compression-controlled section. So we can get that point where we switch from tension-controlled to compression-controlled. And finally, condition 4, but the bottom steel strain is then set to its limit for a tension-controlled section. So the bottom steel strain is yielding, and we can get that value. And this is going to be the final screenshot showing the yielding of the strain. Note that these values might be slightly different in our case if we're using 40 KSI bar. I'm assuming they're using 60 KSI bar, or you can see that they're using 60 KSI bar based on the numbers they have in this example. Now, in this final bit, we will find our maximum and minimum axial capacity, and then we can plot the interaction diagram. So remember the shape of the example diagram, which I've drawn out here for you. The maximum and minimum axial loading will occur at both points the moment is 0. Right, because moment is our x-axis. We can find the minimum value by setting the steel stresses equal to their tension limit. Negative Fy, to calculate the steel tension forces, and then setting the concrete compression to 0. Essentially, the member is at maximum tension in this case, and we can use these numbers to calculate the terms to arrive at axial load. So we see in magenta below, moment cancels out to 0 as a final sanity check. We can find maximum by setting both steel strains to the concrete compressive limit of 0.003. Essentially, the member is in complete compression before yielding. We then use these numbers to calculate the rest of the terms to arrive at what our axial load would be. And the rest of the plot is then filled in with the values calculated before. So the final step of the process is to plot the interaction diagram and demand. And to do this, we need to calculate our axial and moment demand loads. This should be pretty easy because it's numbers you already have from before. The axial demand is just the vertical force on a single column, calculated earlier as the sum of the backstay and mainspan vertical components. So we have 1.2 PV dead load plus 1.6 PV live load. And the flexural demand, or moment demand loading, is going to be the moment on a tower column, both calculated using the governing LRFD load combination. So 1.2 M dead load plus 1.6 M live load. We can now plot these points on the interaction diagram to make sure our tower column passes the combined bending and axial loading check.